Induced drag is an undesirable byproduct of lift. Wingtip vortices modify upwash and downwash in the vicinity of the wing, and these changes in the relative airflow produce a rearward component in the lift vector known as induced drag or lift-dependent drag. At low indicated airspeeds, IASs, the angle of attack will be greater than at high speed, and this will produce stronger vortices. The stronger the vortices are, the greater will be the induced drag. The airflow over the top surface of a wing is at a lower pressure than that below the wing. The two flows are modified by this pressure differential, which creates a spanwise element towards the root on the top surface and towards the tips on the lower surfaces, and these flows interact at the trailing edge and wingtips. In the conventional view of the aircraft from the rear, the vortices produced by this interaction rotate clockwise at the left wingtip and anti-clockwise at the right wingtip. At lower IASs, and therefore higher angles of attack, the decreased chordwise vector and increased spanwise vector, due to the greater pressure differential, will increase the resultant spanwise flow, making the vortices stronger. Wingtip vortices create certain vertical velocity components in the airflow around the wing, both in front of it and behind it. Compared with the relative airflow, the vortices increase upwash and downwash over the outer portions of the span, which reduces the effective angle of attack. If we look at this effect in cross-section, the vertical velocities can be seen to be greatest close to the wing where the vortices are strongest, and immediately ahead of the wing. These vertical velocities, then, are a function of vortex strength. So the stronger the vortices, the greater the reduction in effective angle of attack. Since TAS is also a principal factor in the relative airflow, these two factors combine to determine the change in effective angle of attack. Because of the localized reduction in effective angle of attack, the overall lift generated by a wing is actually less than it would be if there were no spanwise pressure differential. And paradoxically, it is the production of the lift itself that reduces the magnitude of the lift being produced. To replace the lift lost by the increased upwash and downwash, the wing must be flown at a higher angle of attack than would otherwise be necessary. The rearward tilt of the lift vector caused by this extra angle is induced drag. There are three main factors which affect induced drag, two of which will vary during flight, namely lift and speed. Taking lift first, it can be assumed that, since induced drag is a component of the lift force, the greater the lift, the greater will be the induced drag. Lift for level flight will equal weight, so induced drag will depend on the weight of the aircraft, a heavier aircraft generating more induced drag. Some maneuvers, for example turns, require the lift force to exceed the weight, the ratio of lift to weight being known as the load factor, or G, for gravity. As lift is greater than weight in a turn, so will induced drag be greater than in straight and level flight. Thus induced drag also increases as the load factor increases. Induced drag will increase in proportion to the square of the lift force. For a constant lift force, induced drag decreases with increased speed. Because as speed increases, the downwash caused by the wingtip vortices becomes less significant, and the rearward inclination of the lift vector is less. Induced drag varies inversely as the square of the speed. The third factor which will affect induced drag, and which will not change in flight, except perhaps slightly with the extension of large Fowler flaps, increasing the chord of the inboard section of the wing, is aspect ratio. The tip vortices of a high aspect wing affect a smaller proportion of the span. so the overall change of downwash caused by the vortices is smaller, giving less rearward tilt to the lift vector. Thus, for a given lift force, induced drag decreases as aspect ratio increases. The induced drag coefficient is inversely proportional to the aspect ratio. From the factors just discussed, and particularly the last, aspect ratio, it can be seen that a high aspect ratio, that is, a fairly long, narrow wing, is preferable for aircraft designed to operate at around Mach 0.8 for the greatest part of their flights, as are conventional high-speed jet transport aircraft. This is because of the relationship between induced drag, lift coefficient, both low at high speeds, and aspect ratio, expressed in the formula CDI equals CL squared over AR. The higher the aspect ratio, the lower the induced drag. We can examine the effect of aspect ratio by looking at the lift curves for various configurations. The starting point is a wing of a typical section, but of infinite aspect ratio, obviously a purely theoretical situation. But if the wing is given an AR of 18, it can be seen that reduction in AR increases the angle of attack necessary to produce a given lift coefficient. Further reduction in AR, shorter wings, will continue to increase the angle of attack required for CL max. Higher aspect ratio wings are more sensitive to changes in angle of attack, but require a smaller angle of attack for maximum lift. If comparison is made between the coefficients of lift and induced drag, again, starting with a theoretical wing of infinite length, we can see that for a given lift coefficient, a high AR wing will have a lower induced drag coefficient than a low AR wing. At the high lift coefficients associated with low IASs, the induced drag is high and increases rapidly with CL. The lift and drag curves for high AR wings show continued strong increase in CL with angle of attack up to the stall, and large changes in CD only at the point of stall. From a practical point of view, there are restrictions on the aspect ratio of the wing in designing an aircraft. A long high aspect ratio wing will impose weight limits in a structure's strength being rigid enough to resist excessive bending. The longer the wing is, the more susceptible it is to any bending moment. Wing bending moments can, however, be reduced by mounting engines in underslung pods and carrying fuel in the wings. Some aircraft have to keep a certain amount of fuel more in their outboard tanks than that in the inboard tanks, known as wing relieving fuel, to reduce the wing bending moment. The weight of the fuel counters the upward force of lift from the outer wing. A high aspect wing, particularly at low airspeeds, will suffer from a reduced rate of roll compared with a wing of the same chord but shorter span. The reduction is caused, only whilst the aircraft is rolling, by the increased vertical tip speed of the longer wing adding to the wing's forward TAS to cause a greater effective angle of attack with its attendant induced drag. The greater the effective angle of attack at the tip, the more will be the resistance to roll. This phenomenon is known as aerodynamic damping, and will be covered in greater detail later in the syllabus. A long wing will allow less wingtip ground clearance in maneuvers close to the ground during takeoff and landing, which could be a significant factor in a crosswind or gusty conditions. The formula for induced drag, as you will see on the screen, is very similar to the basic lift and drag formulae. On first sight, the equation would seem to imply that induced drag, dI, increases with speed. However, the induced drag coefficient, CDI, is proportional to the square of the lift coefficient, CL squared, and inversely proportional to wing aspect ratio, AR. To maintain a constant lift force, as speed increases, CL must be reduced. Thus, with an increase in speed, CDI actually decreases. We can work through an example, which illustrates the change in CDI with speed, which leads to the change in DI. If an aircraft's speed is increased from 80 knots, 41 meters per second, to 160 knots, 82 meters per second, the dynamic pressure will be 4 times greater. ISA sea level density is used here, but any constant density will give the same result. Referring to the lift formula, lift equals Q times CL times wing area S. If dynamic pressure is 4 times greater because speed is doubled, CL must be reduced to 1/4 of its previous value to maintain a constant lift force. If we apply 1/4 of the previous CL to the CDI formula, then the new CDI equals 1/4 CL squared over AR. And as AR is constant, CDI equals 1/4 squared, or 1/16 of the previous CDI. If 1/16 of the previous CDI is applied to the induced drag formula, we get induced drag equal to 1/4 of its previous value. The conclusions are that if speed is doubled in level flight, dynamic pressure will be quadrupled, CL must be decreased to 1/4 of its previous value, and the induced drag coefficient will be 1/16, and the induced drag 1/4 of their previous values. If speed is halved, dynamic pressure will be 1/4 of its previous value, CL will need to be quadrupled, CDI will be 16 times greater, giving 4 times the induced drag. From what you have seen in this lesson so far, you will know that induced drag is low at high speeds, but at low speeds it comprises over half the total drag. It has also been shown that a high aspect ratio wing reduces the strength of the wingtip vortices for a given lift force, but that there are practical restrictions, both structural and aerodynamic, on very high aspect ratio wings. So other methods of reducing vortex strength have been devised. A flat plate mounted vertically on the end of the wing will restrict the flow of air from the high underside pressure to the low upper surface pressure, and has a similar effect to a high aspect ratio wing, but without the associated bending loads. However, the plate itself can cause parasite drag, and at higher speeds there may be no overall drag saving. Fuel tanks mounted at the wingtips will have a similar beneficial effect to end plates in reducing induced drag, with the added benefit of a reduction in wing root bending moment. Probably the most widely seen method of controlling wingtip vortices is the winglet, which is now incorporated into many categories of aircraft, large and small. Small vertical or near vertical extensions of the wingtip are shaped and angled to the induced airflow, generating a small forward force, or negative drag. Winglets also partly block the flow of air from lower to upper surfaces, reducing the tip vortex strength. The small vortex created by the winglet also interacts with and further reduces the strength of the main vortex. Finally, simpler variations of wingtip shape, such as turned up or turned down tips, can be used to reduce induced drag. Vortices are weakened by the blocking of airflow from lower to upper surface round the wingtips.